So first of all, of course, thanks to Karin and everybody else that organized this workshop for inviting me here. It's always a pleasure coming here. Even though I have to say this is a little bit of a squandary for me because I'm more than happy to tell you about magnetic skyrmions. And I will also tell you how some people at least think they are useful for neuromorphic computation. I'm not necessarily one of them, so but yeah, we'll see how it goes. So anyhow, so first, since this is the first audience, I'll tell you a little bit about magnetic skyrmions, what they are, and then I'll tell you two, since it's supposed to be tutorials on some basic phenomena on how you can move them around, which is presumably what you want to do for many of these applications. I'll tell you how you can generate them in various ways. And then, as I said, in the end, I'll show you how this may relate to neuromorphic stuff, and we'll see. Before I start, I want to first advertise something that many of you might be actually aware of. I also wear a separate hat. I'm an associate editor with Journal of Applied Physics, and as such, I was involved in getting this special topic going there in this journal about new physics and materials for neuromorphic computation. And Julie was actually gracefully one of the guest editors, the one that did most of the work for sure, compared to the other ones, if you see at the other ones. But so this is officially online now, even though this is clearly the future. So check it out. There are a couple of tutorial articles, perspective. Actually, quite a few of the people sitting in this room contributed to this, so you may find yourself there. Anyhow, and in the future, it should be actually a little bit easier to track, hopefully in a couple of weeks or so. With that, let me start now talking about magnetic skyrmions. This is going to be in some way an abridged version of this review that we recently wrote. So if you like what I'm talking about and you want to learn more about it, I can very highly recommend this one. It has all kind of information there in much more detail than what I'm going to tell you about. So magnetic skyrmions is a story that in earnest started about 10 years ago, I would say, with the experimentally discovery of magnetic skyrmions. And essentially what happened is a group from Germany and Switzerland, they did neutron scattering on a compound called manganese silicon, which has been a compound that has chiral magnetism and was well studied already in the 70s and all. And since that time, it was known that it has this peculiar phase diagram. If you look at temperature versus field, somewhere below 30 Kelvin, it orders magnetically. At low fields, it develops a helical magnetic order where the magnetization essentially just rotates around, like such. Then if you apply a field, this spiraling magnetization kind of tilts upwards, so it rotates on a cone. So it has a net magnetization associated with it. And then at some intermediate fields close to the ordering temperature, there was another phase that was known as the anomalous phase because nobody knew what it was for quite a while. And then in these measurements, they did neutron scattering measurements in this field and temperature range on this material, and they saw this peculiar six-fold scattering from the neutrons. And presumably, as far as I understand the story, they really hadn't intended to look for skyrmions. They had the crystal oriented in the wrong way or the field in the wrong way. And what happened is that the six-fold symmetry really doesn't match on the crystal symmetry of the material. And so there was lots of head scratching what this is all about. And after they scratched their heads long enough, they figured out that this corresponds to a magnetic structure that looks kind of like this, where most of the magnetization is aligned with the magnetic field. And then in between, you have like lines of magnetization that point opposite to the magnetic field. And in between, the spins really point in every possible direction. And what makes this magnetic structure peculiar is that it has a very distinct topology. Now, topology is this field of magnetism where people like to map things on other things and see how it doesn't change when you map it around. One way, if you're into this kind of stuff, how you can envision that is topology non-trivial is you can take this magnetic structure and project it onto a unit sphere by putting the magnetization in the center at the south pole, the magnetization at the perimeter at the north pole. And what you then see is that this magnetization wraps once around the whole sphere. It points in every possible three-dimensional direction. And as such, you cannot easily transform it into a magnetization that's all parallel, the fully ferromagnetic state, which you get when you really crank up the field. And it's also topologically distinct from these other structures. Now, you can mathematically actually quantify this. You can calculate the so-called winding number, which is also referred to as topological charge, which you get by evaluating this integral of the magnetization. This is m is the unit vector of the magnetization direction in your structure. And if you do this over such a magnetic structure here, you get a topological charge that's either plus or minus 1. It's plus or minus because if you look with this definition, it depends on the direction of the magnetization. It's odd in the magnetization. If you reverse the magnetization, you also change the sign. So it's with respect to the field that you apply in some sense. Now, the fact that it has topological charge actually generates a little bit new physics, and that's the initial excitement about skyrmions. Namely, if you now take such a magnetic material where you have a skyrmion, and then you take an electron that moves through such a skyrmion spin texture, and if the spin of the electron then adiabatically always follows the local spin texture, it means that actually the spin rotates around as you move it through such a spin texture. And in essence, it's a little hand waving, it's more complicated than that, but in essence, essentially, it means that the electron sees an emergent magnetic field that gives rise to this spin rotation. And you can calculate it, and it turns out this emergent magnetic field is just given by this topological charge. The field that you get is the magnetic flux quantum divided by the area of such a skyrmion. And it turns out that these fields can be rather large. So these skyrmions that were initially measured in manganese silicon are of the size of a couple of tens of nanometers. And if you plug this in here, you get a magnetic field of the order of 100 Tesla. If you have skyrmions that are of nanometer size, it's actually of the order of 1,000 Tesla. And there's a physical consequence to that. One thing that happens is that in this virtual magnetic field, the electron actually gets also deflected, and this is known as the topological Hall effect. But as this electron gets deflected, there's of course also a back action on the skyrmion, which can move the skyrmion. And so this is what initially got people very excited, that you can move skyrmions with very low currents. If you look at these crystals, at these bulk materials where you have these crystals of skyrmions, it turns out that you can move skyrmions with current densities that are 6 to 7 orders lower than what you typically know for using a domain wall. Now, this may not be the newest numbers, but close enough. Now, I should also say, just as a word of caution, if you move them with very small currents, they also move really, really slowly. So this may not be what you want to do for an application. But that's a different story. So now it's no surprise that these structures were discovered in magnetic materials where you have actually chiral exchange interactions, because they help stabilizing these magnetic structures. And let me show this in a very simple way. I apologize for the people that do algorithms and things, but the way how in the physics world we like to think about how things work, we write down a Hamiltonian, which describes the energy of a system. And for a ferromagnet, it's well known that you can use something which is known as like the Heisenberg exchange interaction, where if you have two neighboring spins, the coupling between is just determined by this dot product and a constant that gives you the strength of the interaction. So if this constant is positive, then all these spins like to be parallel to each other, and so you get a fully ferromagnetic state. You know, this is something we all know reasonably well. Now, if you have a material where inversion symmetry is broken, then you can also have another type of exchange interaction between neighboring spins that depends on the cross product. And this is known as the Jaluzinski-Maria interaction, or the asymmetric exchange interaction. And so now the low energy state of that interaction is given by the magnetization being perpendicular to each other, and with a specific direction of each other. So if the first spin is this direction, then the next one would like to be, you know, on one side and not the other, depending on the sign of this constant. Now, if you have both of these interactions in your sample, typically what happens is the spins are neither parallel nor perpendicular to each other, but they're at some intermediate angle, which just depends on the relative strength of these two interactions. And so this is how you get these helical spirals, which, you know, in these chiral magnets were known for decades. Now, something else you should notice, though, is if you only have these two, you of course get equal number of spins pointing in one direction as the other direction, because there's no preferred direction per se for the magnetization. You can change that by applying a magnetic field, which, you know, puts a preferred direction for the magnetization in the system. And in this case, you then can get these skyrmions. And one way how you can think about it is you can have several of these helical structures interfere, for example, in which case you get a skyrmion lattice and so on. So it means that having these Jaluzinski-Maria interaction helps. It's not necessary. You can actually get similar structures without, but if you have it, it's easier. But it requires symmetry breaking, which in these bulk materials you just get by this crystal structure. So manganese silicon is a material that has so-called B20 structure, which is a simple, relatively simple cubic system where the alternating elements are different 1-1-1 planes, like you see here. It's like manganese silicon, and so on. And just by visual inspection, you see this is a different atom than this one, so there's no inversion symmetry. Another way how you can break inversion symmetry is actually by simply having an interface in your structure. And it turns out, this is of course an easy way. You can put an interface on any material. And if you now combine a ferromagnetic material with a material that has strong spin-orbit interaction, which typically means heavy element materials, you can also have a strong chiral exchange interaction at this interface. And this has been shown now in many different systems. Some of the first ones were iron and iridium, cobalt, platinum, permalloy, tantalum. You know, you can combine anything with anything and you get something interesting almost there. Since this is a tutorial, I figured I should say one word of general difference between these two. The way how this chiral exchange interaction comes into play with slightly different symmetries and direction. And so typically, if you look at a material that has a bulk Jaluzinski-Maria interaction, you get a skyrmion structure where the spins in between the center and the perimeter are pointing radially along the direction. So it's what they call a vortex-like skyrmion, or a Bloch-type skyrmion, because if you make a cut from here to here, this resembles what is known as a Bloch domain wall, where the magnetization rotates in the plane of the domain wall. In these interfacial systems, the spins in between point radially out or in, and this is known as a Néel skyrmion or hedgehog. Now, for all practical purpose, no, not for all practical purpose, but for in terms of the topology, it really doesn't matter that much. And so this is, as you said, you can take these structures and project them onto these spheres. In one case, you see that at the perimeter, at the equator, the spins, are around this way. And you can easily transform one and the other, by using a comb and straighten them out or something. So since you can transform one into the other, they're topologically equivalent, and in that sense, it really makes no distinction. So the topological charge for these two is the same. Also, note the topological charge is also independent of the sense of rotation of the spins here, which is some confusion that some people have. Now, having said that, magnetic multilayers is certainly a very versatile system where you can generate these skyrmions. And while the initial work on bulk materials was at low temperatures, now there are bulk materials where you can get it also at elevated temperatures, above room temperature. But multilayers have a much more flexible playground in this way. And there are lots of examples. Our own work where we use cobalt iron boron sandwiched between tantalum and tantalum oxide. Work in France with single layers of cobalt between platinum and MgO. You can repeat these structures and make multi-layers, in which case the skyrmions actually become somewhat smaller. Here are some of the examples of first works along these lines. Well, as I said, you can even have bulk materials where skyrmions can be stable at room temperature. So if you envision an application that you want to do at room temperature, any of these material systems are fair game. Now, one thing why you might want to go from a single to a multi-layer is because it helps you to make things smaller. I show this as an example here of our own work where we put platinum, cobalt, iridium, and have various numbers of repetitions. And you see these are MOG imaging. If you make it thick enough, they're too small for MOG, then we use Lorentz TEM. But you see that the size goes from around a micron for very few repetitions to around 100 nanometers, and people have shown 50 nanometers. And if you use totally different materials, presumably even at room temperature, you can go down to 10 nanometers these days. Now, one of the initial excitement about using skyrmions was that you can move them around, and so maybe that's one way how you make them useful. There are a couple aspects of moving skyrmions that are interesting. Since they are a fairly localized magnetic structure, they can kind of easily move around defects. And so therefore pinning, at least in principle, may not be much of an issue. The other thing, which turns out is quite nice in these magnetic multilayers. In these magnetic multilayers, you also have different ways, different mechanisms by which you can drive these skyrmions, and I'll come back to that later. But early work already showed that indeed, if you put a skyrmion in your computer simulation and put a little defect in your wire, the skyrmion can easily move around it, and just if the current is very low, it actually gets pinned at these structures. So this idea that pinning is not very important, came on early on.
I'm sorry, what's the driving force?
Sorry?
What's the driving force?
The driving force? I'll get back to that in a moment. It's electrically. So in this simulation, the idea is a little bit more complicated, but essentially using electric current, you generate spin accumulations which manipulate the magnetic structure, and in this case, lead to the skyrmion being moved in the direction of the current. But I'll get to that in more detail in a moment. Now, the idea of using magnetic structures and moving them with electric currents and using that for applications is not necessarily new. This is something that was developed as an idea by Stuart Parkin at IBM. And essentially, he had this idea, if you take a magnetic wire, you can use electric currents to move domain walls. And then you can locally read out when a domain wall passes by, and you can use this as an information storage device. I mean, in many ways, it's like an old-fashioned VCR tape, if you want, except instead of moving the whole tape, you just move the magnetization inside of the tape. Now, this is not so easy. Otherwise, you would have this in your computer already. But since this idea was already out, it's a simple step to say, well, maybe we can do this with skyrmions, where we encode information in the absence or presence of skyrmions. And then as we move them around, at least in a computer, you can all move them nicely together. I'll show you at the very end some of our own movies that don't look anything like this. The advantages, presumably, is that skyrmions can be small, of the order of 10 nanometers. They move in the interior of the wire, so their motion may not be as much affected by defect that you may have at the edges. Maybe that makes things easier. It's not clear to me that there's some real advantage to me using skyrmions over domain walls for at least this type of application. There are other ideas where you move skyrmions in 2 dimensions that you cannot easily do with domain walls. That may be more interesting. Now, so how do we move these skyrmions? Getting back to Massimo's question. So I want to tell you a little bit how magnetization dynamics works and how it interacts with electric currents. So if you look at how magnetization changes, this is described what is known as the Landau-Lifshitz-Gilbert equation. It's a fairly simple equation in a sense. The main part is that you have the magnetization on which there is a torque given by an effective field, which consists out of lots of terms. The fields that you apply, the internal fields that you may have due to anisotropies or interaction with nearby magnetization, and so on. But in essence, the magnetization then precesses around this field that the magnetization sees. There's a second term, which is the damping term, known as the Gilbert damping term. At this point, I'm obliged to say that Gilbert worked for a short term in his life at the Argonne National Lab, although this Gilbert constant came before he worked there. So this torque, what it does is it dissipates some of the energy of the precession, which then ultimately leads the magnetization to spiral in and eventually align with the effective field. Now, if you have electric currents acting on the system, you can add one more term to it, where you have spin currents generated by electric currents that then give an additional torque. And there are essentially 2 torques that you can get. If you really want to know the details, the expert is sitting there, so I hope I don't say anything that goes against the grain. But you can have one torque that has kind of the same symmetry as this one, which is then known as a damping-like torque, and another torque where the spin accumulation that you generate acts like an effective field, and therefore it's called a field-like torque. And this is for a very specific case where you have a spin current going across an interface, and there are things like how well the spin current is transmitted and the interface are built into this. But in principle, these ideas work in several ways. You can either pass a current through your magnetic structure, which then generates some of these torques that act on the magnetization, or which in this context, if it's even more important, is you can take a material where spin-orbit interactions give rise to a spin current that are perpendicular to the interface with this material, and the spin accumulation that you drive into the ferromagnet give rise to a torque. And this mechanism is actually very, very efficient for doing this. Now, once you have this equation, you can actually describe the motion of skyrmions using this equation. And one way how you can do this is by using the so-called Thiele equation. The Thiele equation you get by using this Landau-Lifshitz-Gilbert equation, and then you add a rigid magnetic structure that you're interested in, let's say a magnetic skyrmion. And if you do this, you get a new equation that looks like this, and this is known as one variation of the Thiele equation. There are lots of other variations in a way. And in the simplified form, there are essentially three terms that are important. One that is a driving force that's given by an electric current. So in this tensor here that describes what force you get when you have a current in the system depends on lots of details, and I'll come to that in the next slide. Then you have a dissipative term, which gives rise to damping and slows down skyrmions, which is given by magnetization damping. And then there's a constant that depends on the exact structure of the skyrmion that you're looking at. And then you have also a gyrotropic force term that depends on the topological charge of your structure. Now, and this gyrotropic force is always perpendicular to the velocity, to the direction of motion of the skyrmion. Now, coming back to this first case, you can look at various ways how you electrically can move skyrmions, and this is discussed in great detail in this paper here. You can use spin transfer torques, or you can torques from spin Hall effects, which is this other version where I said you have a half metallic, heavy metal layer that then imparts torque on the neighboring ferromagnet. You can look at whether you have the symmetry of skyrmions with interfacial DMI, which gives you these Thiele skyrmions, or whether you have bulk DMI kind of configurations. And depending on the symmetry of the structure, the velocities are either along the current or perpendicular to the current, and also depending on the driving force. And so you can look it all up in detail. Now, for the case that we'll be mostly interested in, is it turns out it's this one, where the velocity is mainly perpendicular to the current that you're driving at. And this gives rise to...
Sorry, so for structures so small, you said these are nanometers, right? And in radii. So
Yeah.
don't you have the large current densities? How come we don't destroy them?
So the large current densities are actually useful because then it means you drive things really fast. And it turns out for many of the applications that you're interested in, you're right, you typically have current densities that are like an order of magnitude away for where you change things drastically. Yeah, but so I mean that's the question: can you optimize materials enough to make this all work? That I think is not so problematic in the end, actually. Now, this is a problem in some sense if you know that the skyrmions move mostly perpendicular to the direction of the current, because it's easy to apply current along the wire. It's much more difficult to apply current perpendicular to the wire. So this is what is also known as the Skyrmion Hall effect, if you want so. So most of you, I'm sure, are familiar with a regular Hall effect, classical Hall effect. You take a charged particle and you move it in the presence of a magnetic field. And there's a Lorentz force acting on your particle, which pushes it sideways from the direction that you want to move it. And you get a charge accumulation at the edges of your wire. You measure that, you know what type of carriers you have, densities, and so on. And it turns out for skyrmions, you have a similar thing, a Skyrmion Hall effect. And so this is an image, borrowed from Karin, who pointed this out at some point, that skyrmions like to move like balls that rotate in air. This is known as a force known as the Magnus force. The structure looks very similar. It's proportional to the topological charge, not the electric charge, but it's still perpendicular to the direction of the velocity. Now, as Karin pointed out, this is very related to the way how rotating objects move. You know this if you're a very good tennis player like Cairo, then you can use this. He's not even in the room. Why did I say that? If you're a terrible golf player, and I don't mention anybody, you know this also. But getting inspiration from when Karin showed these things, I figured I'll show you this example of an expert on the topic. His name is Roberto Carlos. Together with some French colleagues, he's demonstrating how this works. So he puts the ball here. His French colleagues try to block him from moving it in the straight direction, but using Magnus forces, he can certainly easily solve that problem. It's much nicer to see here. Now, you may ask yourself, excuse me, how has any of this anything to do with skyrmions? What's rotating there? Well, so the fact of the matter is, if you move a skyrmion in your magnetic material, of course you don't take all the spins and move them. What you do is you locally rearrange them so that the structure as a whole moves. So if you take a skyrmion from here and move it in this direction, what you have to do is, if you look careful, is the spins on the top side of the skyrmion have to move counterclockwise in order to make the skyrmion move this way, while the ones on the bottom have to move clockwise. Now, this, in essence, looks like the magnetization is locally exposed to a field that points in the plane on the top, which makes the magnetization rotate that way, while it's opposite on the bottom. You don't have to take a picture, you record this. You can watch it, that's just you want in the end. Anyway, so essentially what this means is you get a magnetic field gradient across the skyrmion, and in a hand-waving way, this magnetic field gradient can then couple to the magnetization in the center, and the gradient coupled to magnetization gives a force that's transverse. And that's, in a nutshell, how this works. Now, you see this, for example, also in a micromagnetic simulation. So the micromagnetic simulation, you solve this Landau-Lifshitz equation numerically. So you can put a skyrmion in the center. You apply then in the computer a current that wants to move it. And initially, it moves perpendicular. And then only as it gets close to the boundary, where it's repelled from the boundary, the skyrmion then starts moving in the direction of the current. You can also, using this Gilbert equation, actually calculate how much this displacement, this transverse displacement should be. The transverse velocity over the longitudinal velocity is given by 1 over this damping term here. Now, alpha is typically of the order 10 to the minus 2. D for very small skyrmions is of the order 1, which means the transverse, it's mostly transverse velocity that you get, by a factor of 100.
Actually, it goes like this, then it stops. Because it goes parallel to the current.
No. So this is also what's driving it. It's driving it in this direction, right? Also, if you look very careful, you see that it seems to accelerate. Part of it is that you have this repulsive force here, which then also gives rise to a Magnus force that acts actually in the direction of the current. That's what you expect theoretically. Experimentally, we actually don't see that. And I don't think I discussed that, but that's a different story. But one of the problems also is that now, in order to move it in the direction of the current, you rely on this repulsion from the edge. So if you push your skyrmion hard enough, you may still push it through the edge, and that's not good. Now, can you see this experimentally? Well, you can. You can take a wide wire, and we generate skyrmions somewhere here. And if you look how they move in the presence of this homogeneous current, you see they all move at some shallow angle downwards in this structure. Now you can look at this in more detail. As I said, when you reverse the magnetization, you change the topological charge. You also change the contrast of your imaging. But you see for one magnetic field, it moves downwards. For the opposite magnetic fields, the skyrmions move upwards. If you look careful, so the motion is like the step-like motion because we use current pulses. And so with each pulse, we move in the same distance in x and y, meaning it's really a very well-defined motion, or what is known as a flow regime. Now you can use much smaller current where the motion is much more irregular. And now it turns out there's no well-defined transverse direction. You see it here, it goes one way, the other way. So now the motion is much more dominated by the defects in the sample. It's known as a creep regime.
There's a question.
Oh, sorry.
What was the temperature of this?
It's all room temperature. I'm only showing room temperature to make things easy.
These are the kind of currents that you said this is for the main wall, so you're back to 10 to the 6 amps.
Well, this is per centimeter squared, not per meter squared. Yeah, so, yeah. No, yes. Okay. So I did say, if you want to move them at appreciable speeds, that you need larger current densities. Yeah. So you can. So we did move them at current densities actually down to 10 to the 4. But they don't move much at that point. Anyhow, the point that I'm trying to make here is, so if you look now at this transverse motion as a function of current, you see at low currents, it moves in the direction of the current. Then the angle increases, and at high enough currents, it saturates. And so here at these high enough currents, we can now compare to the simple theoretical calculation what you expect. And so from this theoretical calculation, you expect 1 over alpha d. Alpha, as I said, is 10 to the minus 2d. It turns out our skyrmions are very large. And for large skyrmions, this value of d may be around 60. You see, depending what model you use, it goes up as you make the size bigger. So we expect in our samples a ratio of 0.83 or 40 degrees. Experimentally, we see 30 degrees. So within the uncertainties of how we know our numbers, that's pretty satisfying actually. I don't work at NIST, so it's easier for us. But what is nice is if you look at this, as I said, this depends on the diameter. If you increase the diameter, this number becomes smaller, so this ratio should become bigger. Indeed, what we can do is we can increase the field from 4.8 to 5.4 Ørsted, at which the skyrmion size shrinks a little bit. We go from 800 to 600 nanometers. And so as we make them smaller, this angle actually becomes bigger in accordance with what you have there. So, it kind of works. And if you have friends in theory, they can also calculate these kind of things and see similar things. So Charles and Cynthia Olsen-Reichert in Los Alamos did a simple calculation where they assume skyrmions as particles, and they put some random pinning in there, and they also see that this transverse motion gradually turns on, and when the driving force exceeds the pinning force, you get this result that you expect from no pinning at all. Now, as I said, this transverse motion may be somewhat of a nuisance, because if you drive your skyrmion through your sidewall, it's lost. One way around that is by coupling two skyrmions that want to go in opposite directions. That's something you can do in an antiferromagnet. It turns out then you move it directly in the direction of the current. Also, presumably, you would move it much faster. Really doing this experimentally is a little bit harder. That's not really being done yet. Couple groups are getting close to something like that. But in principle, that's one way how you can avoid that. So now, after I told you a lot how you can move skyrmions, if you want to really make an application based on skyrmions, you have to make them somehow. And you want to make them on demand. And the first step in this direction was 5 years ago in the group from Roland Wiesendanger, where they took an iron-palladium film, an iron-iridium film on top of palladium. No, the other way around. Iron-palladium on top of iridium. And locally, they injected a spin current using a spin-polarized tunneling microscope. And that allowed them to generate skyrmions where there previously were none. And they could also erase them. And so this is exciting, because now you can really start thinking of using topological charge instead of electronic charge to encode information in some ways. Now this is very hard though. There's only a handful of groups that know how to use a spin-polarized scanning tunneling microscope really well. This was done at rather low temperatures at very high fields. The skyrmions that were generated here were typically at defects, so it's not even clear that you could move them around if you wanted to. So a whole bunch of questions there. but it at least showed that you can generate skyrmions and demand. And it turns out that if you have inhomogeneities in your samples, it's really a good nucleation point for skyrmions. And this was actually nicely illustrated here in some simulations that Karin and her colleagues did. They took one of these skyrmion multilayers in the computer and locally changed the anisotropy so that locally the magnetization likes to be in plane instead of out of plane. And so you see this here, this kind of in-plane structure. And if you now drive a current through this, what happens is that by this current passing through this inhomogeneity, it puts some torque on there, and it spins things up, and this defect spews out pairs of skyrmions and anti-skyrmions, periodically like this. It's actually quite neat. And then they go to, and vanish at some point, and what have you. Now, this is if you don't have any additional chiral exchange interactions that give preference to one structure over the other. If you now put Jarzynski-Mourier interaction, you see that one becomes stable, the other one kind of vanishes, and you can, in the computer, you can do lots of things, much easier than in the experiment. You can also use an anti-Jarzynski-Mourier interaction, which makes the magnetization spiral the other way around, and in which case you stabilize the other pair, and the skyrmion vanishes. Now, we did something kind of like this a couple of years earlier using tantalum, cobalt iron boron tantalum oxide. Now, here's a wire that's 60 micrometers wide, a constriction of 3 micrometers here. And so we have these band domain structures that we can push with a current through this constriction. And so here we don't have an inhomogeneity in terms of the magnetization, but we have an inhomogeneity in terms of the current and an inhomogeneity in terms of the spin orbitals. So fundamentally, I think the mechanism is very similar in a way. And if you now pass the current, what you see is that you do generate skyrmions here regularly. It's kind of neat. If you see that these skyrmions really behave like individual particles, they have apparently repulsive interactions between each other. And so you can look at this for quite a while and have fun. So the way how we understood it at the time was slightly different. We know that if you have a domain wall in these structures and pass a current, this domain wall moves with the current very nicely due to spin Hall effects and spin orbitals. Now, if you have such a band domain, then only the top of the band domain is moved by the current. The sidewalls are unaffected. But if you now put this band domain in a structure where the current is divergent, then where the current is passing through the sidewalls, it also puts some pressure on the magnetization domain wall, and it essentially blows it up. And just like what you know when you have a dropping water faucet, or if you blow a soap bubble, as you blow things up, at some point you get kind of like a necking instability, and you whip off a bubble this way. And you can get unlimited numbers of bubbles by this mechanism from this one domain wall. Now, when we looked at this, you can do this with the current going one way, where you get the bubbles on one side, the current going on the other side. You create the skyrmion bubbles on the left. If you reverse the magnetic field direction, you see you change the contrast, but you still generate bubbles just the same way. You can make a little phase diagram that, as a function of field, how much current you need. And you see that at low fields, you need higher currents. And at higher fields, you need lower currents to generate these skyrmions. You can do this in different structures. Whether the constriction is narrow or wide doesn't really matter. Even for wide ones, you get it. You may need a little bit more current. The shape also doesn't really matter all that much. It's a fairly robust and common mechanism. Now, we tried to simulate this micromagnetically which for those of you that do this kind of stuff is a bitch for the materials that we were looking at, because the magnetic structures were rather large, so it's computationally intensive. So we made our structure much smaller. There's not a whole stripe that fits in, but we can get the domain wall here. As we drive it, it becomes at some point unstable, and you start ripping off structures similar to what I described before. And when you switch off the current, this domain wall goes back, and you have a single skyrmion, for example, left there, which interestingly likes to spin around a lot. Now, when we did a simulation, we thought, okay, how about we crank up the current, which in the experiment we were careful not to do because we didn't want to destroy our sample. And it turned out when in a simulation we cranked up the current, with the current applied, at some point the magnetization was all in the plane, and there were no domain walls anymore. And if you switch off the current, then out of this mess, you can still nucleate new skyrmions. So this is very different from the other mechanism, where instead of ripping skyrmions off existing domain walls, you just create them out of a big mess in a way. It turns out this actually works. What we can do is we can take this magnetic bridge away in our samples, replace it with a gold bridge, and now when we use current pulses, with each current pulse, come on, there we go, now. There. With each current pulse, you can now generate skyrmions out of nothing. So this is now where I'm at the point of this tutorial where I tell you how all of this is useful for neuromorphic stuff. So definitely it's not my work, but I'll tell you what others are thinking. Now, we've seen something like this before, right? This is the basic neuromorphic idea. You have a neuron that integrates kind of the signals that you get from different synapses with some weight. And then if you pass some threshold or so, you generate an output signal. And that's like the basic building blocks of how I understand even the algorithms work and all, right? And so one thing that's kind of curious, I think it was mentioned nicely yesterday, you can have lots of different transfer functions. And from, you can have like the simple steps, something that looks more like a Langevin function. If you look at this thing, you can have crazy-ass functions too. There's lots of things used there. And from what I understand, you not only in these algorithms want to change like the synaptic rates by which information is passed on, but also want to tune the transfer functions. Is that about correct? Yeah, maybe. So one of the things that you might want to ask yourself, are there similar nonlinear interactions with skyrmions that you can use for generating transfer functions of this sort? So if you look back at what I've just shown you, well, here we have something that's nonlinear. It's like a step. It looks similar to some of the transfer functions that we've seen. Not sure this is the most useful one, by how much you move it transverse. But you can actually tune it by having different type of impurities. You would change the shape of this curve, for example. Also, the generation is like a threshold kind of event. You need a certain threshold that you have to overcome to make skyrmions. So it's also kind of reminiscent of these kind of things. So in general, any kind of pinning event gives you a natural threshold. And so there are lots of device ideas that come around this way. Now, so the beauty of skyrmions is you can do micromagnetic simulations easily, and it looks kind of pretty, and there's lots of examples published. So here's one that I thought was kind of interesting. Not very practical, maybe, but interesting at least to convey some of the basic ideas. Where here, it was suggested that if you take a domain wall that's locally pinned at some defects in a wire, if you have skyrmions pushing against this domain wall, they may depin this domain wall. And sure enough, in the micromagnetic simulation, this works. You can do this for different current densities. And you see if you have 3 skyrmions that you bring in from this side, then at a certain current density, it's not enough to depin the domain wall. But if you crank up the current a little bit, then you can depin it. So you have this kind of threshold that you envision. what I think is interesting is if you have a different number of skyrmions, like 4, now you need less current to depin this, which can kind of make sense. You have like more skyrmions pushing, so that helps. So you can have now a different depinning current as a function of number of skyrmions. So you get a tunable transfer function. So maybe that's useful in some way. I don't know. Although, as I said, this particular example is probably hard to do. But the same basic idea you can expand in many other ways. Here's an idea where it was suggested that you can have a step-like change in a barrier here. And if you look at this paper, there's lots of things that sounds like biology. But it's the basic idea. You accumulate lots of skyrmions before the barrier, then you can push it across, and it looks like this integrate and fire type of functionality. In a different vein, there's a suggestion of making materials that you have like graded thicknesses, which then continuously tune things like anisotropies and Jasinski-Murray interactions. And so what that gives you, it gives you a very shallow angled potential where if you put a skyrmion in here, it really likes to be on this side. If you now use a current pulse, you can move it to the right. If you switch the current pulse off, it slowly kind of walks back. So it's similar to this kind of relaxation stuff that we looked at yesterday. So if you just have one pulse, it moves and then it goes back. But then if you have lots of pulses, and they are fast enough with each other, they may finally push them to the end, and you declare then, if it comes to here, it fired. So it's another of these integrate and fire kind of ideas. Now, another thing, I promised Mark every talk has to have something like this at some point during this meeting, otherwise it doesn't really count. So you have this idea of reservoir computation, where you feed your input into your physical system, and then the physical system does something complicated, and at the end you get something out. Now you can do this also with skyrmion in some sense. You can look at the dynamics, and this is very similar to what Julie and colleagues have done in spin torque oscillators. Skyrmions have their own very well-defined dynamics. One is the breathing mode. And so here the idea in this paper is that if you now feed spikes of magnetic field pulses that excite the dynamics, if you do it in the right timing, you may then add them up and increase the amplitude of the excitation. And you define a certain amplitude of the excitation as a threshold where things fire, I suppose. You can also come up with something different. And this was done here in some sense, where you have like a complex arrangement of skyrmions and other things, and really just a very complicated domain structure there. And because of that, the way how current flows through the system is related to the local magnetic structure. So you get a very inhomogeneous current flow. Now, if you modulate this magnetic structure, you may change this current flow in some complicated ways. So this almost looks like this picture there. I think that's the inspiration. Now, in all honesty, the changes of the resistance are really rather small. So whether this is a practical way of doing any of this, I'm not so sure. But there may be always more clever minds than me. Now, one other aspect that inspires people to think of skyrmions for this neuromorphic computation is that in a way it's a noisy system. And you see this here. This is one of our early measurements. Here we use current pulses. And so with each current pulses, we can generate lots of skyrmions. But now there's no current. And you see they move around. And then there's another current pulse. You get a totally different population of skyrmions. And they still kind of wiggle around and move around. This is actually not very good if you want a racetrack memory, to say the least. But lots of people are good at making lemonade out of lemons. So one idea is, well, if they move around, we just use this diffusion for some stochastic purposes, and so you were involved in this. So here the idea is you can generate a random stream of skyrmions coming in some area. In this area, they can move around in some random way. And if densities are always concerned, that means you have as many skyrmions moving out as you put in, but in a very uncorrelated fashion. And being able to uncorrelate signals is, as far as I understand, one way how you can do computation. And Danielle, can you tell more about this for sure? So by combining two random streams, it's effectively like multiplying numbers, and so you can see how you can do computation like that. And indeed, something like this was demonstrated here in these halls somewhere. A structure, it's very faint to see, but this really actually is something like this. And here, magneto-optically, they look at skyrmions coming in, and they count this as signals. And if you look at it, this doesn't necessarily have the same time structure as that, but more or less the same probability. Now, that's another way how maybe you can use skyrmions for neuromorphic kind of ideas. I should say that using these big bulbs there probably wasn't necessary. I think if you would have just looked on a single wire, you get something very similar. So we've done things where we put skyrmions in a wire, and if you now pass currents through it, at low enough currents, you see that the motion is all stochastic, defined by local defects. And so for sure, the rate how skyrmions move is identical everywhere in the wire, but probably the actual time structure is fairly random. But this also illustrates you can have lots of fun with skyrmions. You can put them in round wires, you can move them around, do this and that. And it's fairly easy to do. If we can do it, anybody else can do it. So have your own fun with skyrmions and see what they're good for. That brings me to my end. This is the group that did most of the work for our stuff. In particular, this guy, Wanjun Zhang, he was the guy that pushed our skyrmion work a lot. He moved on now. He's now at Tsinghua University in Beijing. Besides him, there were a whole bunch of other postdocs, Wei Zhang, Benjamin Jungfleisch, that were involved. More senior stuff, most notably Ola Heinenen, who did some of the micromagnetic simulation, and Susanne Feldhaus, who was really in charge of all the magneto-optic imaging I showed. For our work, we got the samples from UCLA and some theoretical support in the beginning. Later, we had some micromagnetic simulations from Yan Zhu in Hong Kong and student Zhao Wang from Bryn Mawr that worked on this stuff. Here's briefly my conclusions. So you can use magnetic skyrmions at room temperatures relatively easy in magnetic multilayers because the interfacial interactions help stabilizing them and gives you lots of room how to engineer their properties. You can move spin skyrmions relatively well using spin-orbit torques, which is a very efficient way of doing it. Now, the topological charge gives rise to gyroscopic forces like the Skyrmion Hall effect, which, depending on how you look at it, is a nuisance or useful, who knows. You can generate skyrmions in a very general way from any inhomogeneity in your spin texture or in your samples, which is actually a nuisance also, because if you have defects in your samples, and I know few experimentalists that don't have defects in their samples, then these defects can randomly generate skyrmions or randomly absorb them, which is bad. But then you can also think of how you can use their nonlinear properties and their stochastic behavior due to thermally driven motion or etc. for purposes that are of interest to this group of people. Well, thank you very much for your attention.